Tim is going to talk about improving service life of reinforced concrete structures using internal curing. So turn it over to Tim.
All right, good morning, good afternoon, good evening, wherever you might be joining us. I do work for GCP Applied Technologies today, but I need to start off by saying that this work actually predates my employment. And so the opinions and the data expressed herein are my own, and they don't represent anything for GCP in that regard. I do have an outline. I think I've got a few fewer minutes than what I had originally planned, so I'm going to move through quickly on all of these items. We'll go through a very brief background and introduction. This work was sponsored by the FHWA, so we'll be focused on bridge decks here today, but the lessons that we learned for internal curing and high-performance concrete apply equally to everything that we're doing here at ACI. We'll go through very briefly the field implementation of internally cured high-performance concretes. I'll show you some of the measured properties. We'll touch on the mechanical, the shrinkage, and the transport properties. I'll actually be sharing some information that relates to what Armin was talking about earlier on the sealed resistivity method and the saturation function correction, and then I'll go through what we're seeing for performance. So I will be speaking very quickly, so if I lose you, there's an outline up top to keep us on track. And so our background and our motivation is that we really have a 75-year design life that's specified in AASHTO. I think the community in general is now talking 75 to 100 years. Those are our target values when we're talking about service life design. When you actually look within the AASHTO LRFD spec, you'll see that when you search for anything related to durability-based design, at least when I was originally doing this a few years ago, you'll find that it actually tells you that if you think you're going to have an issue, you might want to think about designing the replacement deck up front. And you actually can go through and you can see that this is in fact what we see in the field. So this is data from the National Bridge Inventory for the state of Indiana. And you can see that when we began constructing bridges back in the 50s with the Interstate Highway Program, and you can see a line offset from that, which is the bridges that we're rehabilitating, which includes bridge deck replacements. And there's about a 27-year difference between those two, and indeed that seems to match up quite well with what they're seeing for the performance of those bridges in Indiana. So as of the 2013, when I originally did this assessment, there was about 19,000 bridges. Only 13% of them had actually achieved the 75-year service life or greater. The cost estimated $2013 to replace all of that, $3 billion, give or take. So just to set a little bit the stage of what I'm talking about when I say service life, really I'm focused on corrosion-based service life. So we're going to be really primarily talking about extending the diffusion portion of the simplified model, where we have just an initiation stage and then a propagation stage for corrosion and reinforcement. And then on the other side of it, we actually do need to take care of the cracking. And so that's something where we're trying to avoid early cracking and really extend the performance. And so it really does go back to, well, this should be simple, right? We should just be able to make better concrete. But we did indeed try that back in the 90s with the high performance concrete experiments. And we found that we had extraordinary early age shrinkage cracking problems. And it turns out that it's driven by the reaction of the concrete itself. And so you get internal self-desiccation. And so that's where the internal curing is going to come in. And then we'll go ahead and we'll talk about the resistivity method as how I would recommend that we are actually implementing a specification to be able to ensure that we're getting that service life. So very briefly, the internal curing is really coming from a requirement of the fact that we have chemical shrinkage with the hydration of cement and water. So when you react cement with water, you get about a 9% volume reduction. When we look at this in a system that's hydrating, you'll measure this over time and you'll find that up to the time of set, the chemical shrinkage is exactly equal to the autogenous or bulk shrinkage. Thereafter, you actually measure a difference between those two values, and that is actually represented by void space creation. We can describe this using a fundamental relationship, and we find out that we are emptying out pores of smaller and smaller radii. And so if we look at a high water to cement ratio system versus a low water to cement ratio, and we lose the same amount of water, which is represented by the yellow shaded areas here, you'll see that the low water to cement ratio systems, we're emptying out much, much smaller pores, and that creates a pore stress generation. So for internal curing, we're going to be focused here on the use of lightweight aggregates. There's a rule of thumb of about 7 pounds of water per every 100 pounds of cementitious materials that we're going to hide inside of the lightweight aggregate. I've got here for you the Bent's equation that's been around for a while, so hopefully most are familiar with it. But there are considerations that we need to look at when we're talking about in the field and actually doing this at production scale. So we don't have a perfect aggregate that is in SSD condition. We have something with surface moisture and then absorbed moisture. So we need to know what the SSD condition is so that we can determine how much internal cured water we are actually providing. And then we need to know what's on the surface, and that's primarily a critical item because if we don't account for the surface moisture on the lightweight aggregates, just not accounting for a very small percentage of that potential moisture, we quickly can exceed, say, a target specified water to cement ratio. So in the field, what we actually have is something like a pile of aggregates that's got a soaker hose on it. You may have been tempted in past years to go out there and try to run the only standard test at the time, which was the paper towel test in the field, and you'd be laughed off the job site if you tried to do that because it takes about 45 minutes and it is not a fun test. And so we actually implemented the centrifuge method, and it's now standardized in Indiana test method 222. All you do is you spin the lightweight aggregates for 3 minutes at 2,000 RPM. And it turns out that indeed it is a very robust method that you can consistently recover the correct value for the absorbed moisture and the surface moisture. The other side of it is the uncertainty in the paper towel method. Actually, if you run the test and you make the correction, the uncertainty is so high that you could still, in theory, be out of specification for a water to cement ratio. And so the centrifuge method does eliminate that issue. For the bridge decks in Indiana, there were originally 4 as a part of the study. There was a couple added after the fact. I won't dwell on this. There's a full report that I would love if everybody would go read that. But what I do want to draw your attention to is the actual in-service life of the previous decks, and you can see that indeed all of them anywhere between 11, the best was 40 years. So it is indeed a problem. For the mixtures that we were implementing, we were looking at a 25% paste volume, a water to cementitious ratio anywhere between 0.36 and 0.43. I believe everything was about a 0.40 for this study. We're providing at least 7 pounds per every 100 pounds in terms of internally cured water. We were following a little bit of a modified approach, so it's not exactly the same as 1761. For the cementitious materials, we were looking at a ternary system, so there was silica, fume, fly ash, or slag, and a minimum cement content. The specified metrics that we're looking at was target air, target slump, fairly trivial compressive strength for this class of materials, and then a RCP value of less than 1,500 coulombs. And so here's just some pictures from that construction, and I will very briefly note that indeed no technology is a substitute for the best practices of construction, and so if you don't have a good pump operation and logistics, you might run into some troubles with both supplying the material and also keeping the fresh properties. But all in all, there were no huge issues related to any of the construction of these bridge decks that weren't outside of just normal practice considerations. For the internally cured portion of the work, some considerations. There had been rumors that lightweight aggregate didn't like turns on belts, and so here's a picture of lightweight aggregate making a turn on a belt. I will note that batch software expertise is really a big one and a critical one because there are some considerations in terms of the amount of surface moisture that you have to plug in and the amount of absorption that you have to plug in, and sometimes you should probably be adjusting bin jog rates. And so I'll just say that the best time to work through all of that is at a trial batch, and most certainly not the morning of construction. During construction, I will also note that we probably need to be, again, doing better practice in terms of things that we shouldn't be doing on any structure. There's conversation about whether or not these bridge decks had a couple of them some scaling issues, and I would say that it's probably going to be hard to determine what the real underlying source of those are, and so we shouldn't be working things into the surface during finishing, primarily because those products are 80% water, at least in a lot of these cases. Going through the experimental data very rapidly here, so we can look at the mechanical properties. We can see that indeed these were all very high strength materials, and in general, the ACI equations within the plus or minus 20% that we would be looking for do indeed apply. So this is not lightweight concrete. In terms of the drying shrinkage, We've measured it here. It's perhaps not the most obvious or best test for understanding the true difference for what internal curing is doing. But what we see in the difference primarily is the mass loss. So to get to an equivalent shrinkage, you have to lose almost twice as much moisture from the specimens. And that's the primary takeaway. And so there's a lot of enhanced robustness to brine shrinkage built in here. Looking at the autogenous shrinkage, so I've got linear autogenous shrinkage on the left, the dual ring test on the right, so restrained autogenous shrinkage. I'll skip over the first one because it was actually an expansive cement. I'll skip over the second one because we did have a testing error on the right with the temperature, so it's not as obvious to see what's going on. And so I'll stop on this one, and you'll see that indeed we have a reduction in the residual tensile stress built up due to the restraint of that shrinkage. You can see that we have different rates of stress generation when we drop the temperature at that point. And then you can see that the total magnitude of the stress is reduced here. So the primary thing that's going on there is actually that internal curing will reduce the coefficient of thermal expansion at very early ages. The secondary contributions that's going on is that there is a slightly lower stiffness. So there's more relaxation in the system. And then I'll leave it at a note of all of this does scale with paste volume. And so here's just a reference for you in terms of what that relative magnitude would be related to 25% paste content. Getting into the actual service life portion of this, so we went ahead and ran all of the tests that are being considered for durability specs. And I'll just simply point out that all of the units for all those tests are very different. And so it does make it sort of difficult to look at it. I will also point out that we blew right past the 1500 threshold. So these were indeed well within specification and quite high performance materials. But perhaps the question maybe more interesting is, can we actually compare these? So I did measure the resistivity of all of these specimens before we tested them so that we had a consistent metric to compare them against. There are a couple corrections for the fluid that you're saturating it with. So I've got that shown for you. And here is a plot, the resistivity, the diffusion coefficient that you get out of that method when applied appropriately versus the other methods. And so we see that the RCP test and the resistivity test give you exactly the same number. You can see that the sodium test, there is a little bit of an offset, and that's because it is a migration test and they're making a back correction for the chloride binding, and then the Nord test does not make any such correction, so that's why it's on a different line. We can crank through with one of those diffusion coefficients in perhaps a nice model for service life. We can set some threshold for the initiation of chloride. We can say this is where our current class of materials are. We can take a look. I think I skipped past it. So the non-internally cured mixtures that were our references, we had a couple that were lower performing and a couple that were high performing. All of the internally cured mixtures, anywhere between 60 and 90 years is what we're estimating the initiation for corrosion is going to be. So we're looking at 60 to 90 years estimated service life for these. I will raise the question of, is there another way to go about doing this? And I would suggest that there is. And so we can use a sealed resistivity method. We can make these measurements. You'll see that those lines are nowhere near one another, and it's because there's a couple corrections that need to be applied. So there's the pore solution resistivity, which I won't talk about here. I will just recommend that it be calculated for the moment. And then there is a correction for the saturation function. So we went ahead and we measured this for all of the different specimens. We chopped the cylinders into 3 pieces, measured all 3 pieces. And then we tried to fit what we thought was the S to the N type of saturation function, and we see that it doesn't really fit. So that made us kind of start to rethink, well, what does it actually mean for air-entrained concrete? And so we've come up with a different model. I've just shown it here conceptually, but actually I've also in my work have gone through a series of electrodynamics calculations that do indeed suggest to support that this is what the shape should be. So there's points of interest. There's the Nick point degree of saturation, which is what the bucket test is getting us most near. And then we have full saturation if we pull a vacuum near 0 torr, where we're filling in the air voids. And then I will just simply note that the sealed degree of saturation is very, very, very close to the Nick point degree of saturation. It turns out that it's about 10% difference on the average from some basic calculations. So what I will just say is that the fundamental value that we should be comparing against is indeed the nick point, because you can see when we treat the air voids as conductive inclusions, the actual measurement that you get is dependent primarily on the volume of the air that was entrained. And so that's a variable throughout production. And so it needs some estimations with powers. And we can see that if you treat just the contribution of the air voids, it itself fits into an S to the N type of relationship. So these are just theoretical calculations. Joe went back and last year they came out with some raw data or some actual data to suggest that indeed that's what they find. So this is the saturation function that I am recommending or proposing here. It's got a lot of jazz going on, but it's essentially treating those three different contributions together. I also recommend that we not chop cylinders into small pieces, because you start measuring the void distribution throughout the height of the specimens. And so it turns out if you just do it on the full 4x8, you get exactly what you're looking for. And then you can apply some statistics to it, and we can come up with an actual coefficient of variation within the testing method. And so when we put all that together, we can turn this around and we can say, well, now I have a target diffusion coefficient that I'm looking at, and we can evaluate relative to that. And so if we actually go through and we start with service life estimations, and we take and we begin varying what the chloride diffusion coefficient is, we can create these kind of response maps in terms of estimated service life. So we can see what the variation from north to south in the state of Indiana might look like, the variation for construction tolerances for the steel depth might look like, and then perhaps a 20% variation just on the actual measurement itself. But what I would say is that what we can do with this type of approach is we can now begin to look at, well, what service life do we want to specify? So we can say 25, 70, 50, 75 years, and then we can come up with either a specifiable chloride diffusion coefficient, or in my mind equivalently, the formation factor, which is being pushed heavily. So we can rearrange these things and come up with a target design resistivity based on the design diffusion coefficient or formation factor. We can correct to the measured value that we expect using the saturation function. We just need to agree on what that is. And then we can apply some statistics to it. And so we did this for one of the bridge decks, the fifth bridge deck. So this is an estimation made at a specific date, 28 days, and we can see that we've, for this kind of cooked up example, we've hit a target value here within the specified distribution, and it equals, I think, about 50-year service life at 28 days. We can look at this perhaps more on a discrete sampling type of basis, so by truck numbers, and we can see what this looks like over, say, the construction of one of our structures. Or if we have the luxury, we can just measure this over time, and we can see when we meet the threshold value that we're interested in. And so rounding the bend here, I will just wrap it up with what we've actually seen so far. So the primary cracks that I saw when I observed these within the first year of construction, there's two structural cracks at an integral pier on one of the bridge decks, and so that's primarily just a design consideration. No sign of any typical regularly spaced transverse high performance concrete cracks. Bridge deck number 2, I will point out that after the first year, we saw that we had some pop out cracking. And so again, best practices still apply regardless of what we're trying to do. So we need to be screening our coarse aggregates appropriately. Bridge deck number 3 looked great. And then number 5 was actually interesting because within the first week, we had something like a 30-degree temperature drop because it was cast in November. There are no cracks in that bridge deck. Interestingly, the safety rails were actually not internally cured because they didn't have the support to do that on their own on a different date later on. And so there are a lot of cracks in those rails. And this goes back to what I mentioned earlier about internal curing, providing a significant boost to the thermal cracking component due to the reduction in the coefficient of thermal expansion from internal curing. So just very briefly, the summary is that indeed these mixtures perform quite well The early autogenous shrinkage was reduced from internal curing. The potential for cracking was significantly reduced. We've estimated that the service life improvement can be very substantial. We should be able to target the 75+ year for design life. And we didn't see any cracking that was indicative of typical HPC issues. And I'll leave it with the group in Kansas has been nice enough to also be looking at these bridges in their studies. And so you can see the green squares are the decks in the study. See the performance relative on top to primarily control specimens or bridges in Kansas, and then relative to the great work that the Darwin group's been doing on the low cracking, high performance concrete mixtures. We're still on the upper end of performance relative to those as well. So just the final word is that indeed I would say that we can specify a 75+ year design life. It is achievable and implementable. And I know we're a couple minutes over time.
Tim, can you quickly go to the Q&A and see if you can answer those three questions, those last three questions in the Q&A box? One's related to the target amount of internal curing water.
So the first one that I'm seeing is recommendations for use of lightweight aggregates for UHPC.
No, the last three questions in the Q&A box.
Last three. Can you provide any suggestions of how to better meet the target about IC water? Some of the Indiana bridge decks had higher than 7% due to the way absorption was quantified when developing. So one of the approaches that perhaps was more conservative was that the DOT did not want the mixtures to be redesigned on the date of construction. And so we weren't able to use the absorption value as the actual absorption value and adjust proportions on the day. It was a meet or exceed. And so that would be the number one recommendation is if you want to be able to control it, you need to be flexible on the day of construction with the method in which you're specifying it so that you can readjust your mixture proportions to reflect the actual absorption values that you do get on the day of construction. That's one way to go about it. The other way to go about it would be perhaps a shorter duration of soaking so that you are perhaps not going too far past the target 24-hour value. The next question.
It's actually the last one about relating the service life to depth of atmospheric carbonation.
So this study and the work that I just presented here, we actually weren't looking at all about the depth of carbonation. So I don't have any specific information that I can share on how that may have been different or changed with these mixtures, other than from the standpoint of there's certainly a lot of work on gas permeability as it relates to the pore networks. And so those same lessons do apply to these high performance concretes as well.